Hi, everybody. This is chapter 5 homework. And in this, we'll be doing problems 1, 7, 10, 22, 26, 45, 60, and 68. Let's begin. Problem 1 reads, two 25-Newton weights are suspended at opposite ends of a rope that passes over a light frictionless pulley. The pulley is attached to a chain from the ceiling. What is the tension in the rope? What is the tension in the chain? For the rope, we have, it's a static, so we have 25 newtons here and T here. And since this is in a state of equilibrium, T equals 25 newtons. For the chain, we have the chain here, something like this, and 25 newtons and 25 newtons. So for the chain, T equals 50 newtons. All right, that was one. Now we're doing number 7. Number 7 reads, find the tension in each chord if the weight of the suspended object is W. And there's 2 diagrams. The first one looks like this. This is W. This is 30 degrees. This is 45 degrees. This is A, B, and C. Okay, so we're going to write some of the forces, all right? And we're going to use our X and Y components. So the sum of the forces in the X is going to be A, tension in A, times a sine 30, plus tension in B times sine 45, minus C equals 0. All right, because these guys, we're going to work about that point right there. So these guys are going up, C is going down. All right, sum of the forces in the Y, you're going to have tension A, cos, negative tension A, cos 30. And you may ask me why we call that negative is because here's the dot, the point about which we're taking the tension, and anything to this going that way is conventionally negative, okay? Plus tension in B, cos 45 equals 0, right? This is the only horizontal forces we have, and they are in static equilibrium, just like everything is in static equilibrium here. All right, so let's see. Oh, I'm sorry. C, we'll call CW. Let's just call CW. We know that C is going to be equal to W. All right, I'm just looking at my solutions. All right, so I'm going to go ahead and start solving. So I've got TA cos 30 equals TB cos 45. And I've got negative, wait, yeah, no, TA sine 30 plus TB sine 45 equals W. And I did it a little bit different from the solutions manual. If any of you guys have that, you can do it. You can actually solve these problems probably in several different ways, but we'll just go with my way. I kind of like it. I went ahead and did TA equals, went ahead and solved here. TB cos 45 divided by cos 30. And I got, let's see, then I went ahead and did TA equals 0.86 TB. Okay, so I went 0.816 TB. And then I went ahead and let's see, I had TB that was from this. TB equals weight over 1.11. So TB equals 0.897 weight. And from that, you can go ahead and solve for TA in terms of weight. And that's the first one. All right. Now, part B looks something like this. You got a corner here. And you've got boom, boom. You got that angle. You got this angle. This is B. This is A. That's C. And this is W. And this angle is 60. And this angle is 45. Let's go ahead and solve this. Let me pause this for a minute. All right, for part 2, I set the equations up for you, and I'm going to let you solve it, but I'm going to explain what I did here. Some of the forces in the Y, A and C, are in the negative direction. So A's got this guy, right? So this will be tension of A, negative tension of A, times the cosine of 60, right? So don't, make sure you, before we were using the sine of 60 when we had this guy, right? Because that was that angle. Now we've got an angle here. So it's the cosine of 60 minus W, because that's the tension on C. Both of these are going in the negative direction, equals TB times the sine of 45. So make sure you note that those two are different trigonometric functions, and make sure you understand why. And then the sum of the forces in the X is going to be, once again, we're using this direction to be negative, TA sine 60 plus TB cos 60. So it's negative TA, positive TB, and they're going to equal 0. And now that you have those two equations, and you have only two unknowns, TA and TB, we're using W as a value. It is actually an unknown, but we're using it as, we're writing everything in terms of W. So we only really have two unknowns, two equations, two unknowns. You can go ahead and solve by TA equals TB cos 45 divided by sine 60. Get a value for here, and then use that to put it here, TA, and then go ahead and solve in terms of W. And I'll leave that to your pleasure. It should be fun. So go ahead and do that. And that was 7. This is problem 10, chapter 5, and it reads, the weight is 60 newtons. What is the tension in the diagonal string, A? And find the magnitude of the horizontal forces F1 and F2 that must be applied to hold the system in the position shown. So what we have here is a ceiling, apparently, something here at 90, something here at a horizontal string. We have a diagonal here where this angle is 45. And then we've got a horizontal here. Obviously this angle is 45. And we have a 90 Newton weight from there. And we need to know the tension in the diagonal string. So what we've got here is, I don't know what we call it, T, I guess we'll call that T. T sine 45 equals 90. So T equals 90 divided by sine 45, which I believe is a root 2 over 2. Let's find that out. On 90 divided by sine 45. It's 90. Oh, I guess it's just 90 square root of 2. I don't know what the square root of 2 is. Let me get my other calculator. On clear, 90 times to power of 0.5. Oh, I'm sorry, that's 60 newtons. Okay, so that's 60. Let me pause and rework this. Okay, this is 60, not 90, 60. This is 62. And this is not 90, that's 60. So it's 60 divided by sine 45, which is 60 divided by sine 45. And that's going to be 84.8 newtons. So the tension there has got to be 84.8 newtons. All right. Okay, so this is T cos 45 is going to be equal to this guy, that one, and that one. So that's going to be 84.8 newtons cos 45. That's going to be exactly 60 newtons. That's 60 newtons. Okay, this is chapter 5, problem 22. It's a calculus problem. It reads, a 2,540 kilogram test rocket is launched vertically from the launch pad. Its fuel of negligible mass provides a thrust force such that the vertical velocity as a function of time is given by v sub t is going to be equal to at plus bt squared, where a and b are constants and time is measured from the instant the fuel is ignited. Okay. The rocket has an upward acceleration, so a equals 1.50 meters per second squared at the instant of ignition, so at t equals 0. And an upward velocity of 2 meters per second at 1 second later. So v equals 2.00 meters per second at t equals 1 second. So for part A, we determine A and B, including their SI units. Okay, so I'm going to go ahead and determine A and B. So what I'm going to do for the first one is I'm going to use this because I love the fact that t equals 0. So one of the terms is going to drop out. So, but I need A, so I need to solve for A. So dv dt is going to give me A, so I'm going to take the derivative there. So I'm going to get A plus 2bt equals 1.50 meters per second. All right. I know t is 0, so that term is going to drop off. So A is going to equal to 1.50 meters per second. Okay, so that's A. Squared, this is squared. Sorry, meters per second squared. That's squared. So A is 1.50 meters per second squared. All right, and now that I know that, I'm going to use my second set of data to determine B. So V is 2.00 meters per second. I'm going to use this equation. Is going to be equal to 1.50 meters per second squared times t, which is 1 second, plus b times 1 second quantity squared. All right, so this is going to cancel out one of those squares. So I'm going to subtract that from both sides. 2.00 meters per second minus 1.50 meters per second is going to equal to b times 1 second squared. All right. So now b is going to equal that divided by 1 second squared. So that's going to go away. B is going to equal 0.5 meters per second cubed. All right. So we've determined A and B and the units. B is going to be equal to 0.50 meters per second cubed. All right. Let me pause, clear my board space, and continue. Okay, so now we have for part B says, at 4 seconds after fuel ignition, what is the acceleration of the rocket? Okay. So at 4 seconds, all I have to do is like take the derivative and solve. So A is the acceleration. A equals A plus 2BT. So A acceleration equals 1.50 meters per second squared plus 0.50 meters per second cubed times 4.0 seconds. And let me just get that. Let's see, what is my answer there? That is going to be 5.5 meters per second squared. So the answer to B is 5.50 meters per second squared. All right, and C wants to know the thrust force. And to solve for that, F equals ma, so I was given m. So force equals mass times acceleration. I'm assuming they mean at 4 seconds. Let me look at these. Let's see. Okay, so the thrust, I forgot about G, is going to be equal to M A plus G. So the thrust is going, okay, it's overcoming G, right? So it's overcoming G to have this. So the force has got to overcome that G. So thrust is going to be equal to 2540 plus the 5.50 meters per second squared plus 9.80 meters per second squared. Right, if I'm accelerating upward at this, I'm overcoming that downward this. So let's see, our answer here is 3.89 times 10 to the 4th newtons. 3.89 times 10 to the 4th newtons. All right. So we're asked to express it as a multiple of the weight. So thrust over weight is going to give us 3.89 times 10 to the 4th newtons divided by 2,540, was it 2,540,540 kg times 9.8 meters per second squared. And the answer here is 1.56 weight. 1.56 W. Okay, finally, what was the initial thrust due to the fuel? The initial thrust was this, right there, 1.5 meters per second squared. So all you have to do, and I'll let you guys solve this on your own, is you go here to this guy and you substitute 1.50 meters per second squared for 5.50 meters per second squared, because we at t equals 0, our acceleration was 1.5. This was our acceleration at t equals 4. And that was problem 22, chapter 5. This is chapter 5, question 26. And it's a long one, so bear with me. It reads, in a laboratory experiment on friction, a 135 Newton block resting on a rough horizontal table is pulled by a horizontal wire. The pull gradually increases until the block begins to move and continues to increase thereafter. Figure E26 shows a graph of the friction force of the block as a function of the pull. Identify the regions of the graph where static friction and kinetic friction occur. Okay, so what we have here is something like this. And this is where the static friction occurs, right here. Okay. And then we have this, the block is moving right here. This is the kinetic friction. Once we've overcome that coefficient of static friction, then we get some motion. And this is the force, this is force. And this is, let's see, this is friction, I'm sorry, this is friction in newtons. And this is the pull, I guess that's the pull in newtons. So the friction increases steadily right here. And then now it starts to move. The friction drops. This is static friction. It's as large as it needs to be to prevent motion. And then when it can no longer prevent motion, we are going to have a steady friction force because that is the kinetic friction after that. All right. So now what do we do? That's A. Find the coefficients of static and kinetic friction between the block and the table. Okay, so we have our maxed out right here at 75 newtons. And this guy, kinetic, is at 50 newtons. Okay, so friction is defined as mu, K, or S, and then times the normal force. And we know the normal force from the problem is 135 newtons and equals 135. So the mu S is going to equal to 75 newtons divided by 135 newtons. And mu K is going to equal to 50 newtons divided by 135 newtons. The normal force doesn't change. Since it's a flat table, it's simply the weight of the object. So this guy is going to be 0.556, 0.556, and this guy is 0.370. And one thing to note here is it is a unitless quantity. These coefficients of friction do not have units. Okay, so that's that. I'm going to pause and get myself some board space and continue. Okay, problem C, I've already explained. It was wanted to know, it wanted us to explain the shape of the graph. Problem D wants to know what happens if we double that normal force right here, right? Well, the coefficient of friction is going to be the same. This guy is the same. So this guy is going to double, right? Because if I hold my coefficient of friction steady but double my normal force, I'm going to have to double this friction is going to be double, right? The friction is a function of the contact force plus the surface quality, okay, plus the coefficient of friction. And that is problem 26. All right, we are doing 545, which says a small remote controlled car with a mass of 160 kilograms moves at a constant speed of v equals 12 meters per second in a track formed by a vertical circle inside a hollow metal cylinder that has a radius of 5 meters. What is the magnitude of the normal force exerted on the car by the walls of the cylinder at point A, bottom of the track, and at point B, top of the track? Okay, well, at the bottom of the track here, let me get you always feel heavier at the bottom of a track, right? So we have N going upward, right? Minus G is going to be equal, mg, mv squared over r. That's the bottom of the track. At the top of the track, your normal force NG are going down, so it's going to be N plus mg equals mv squared over r. So for that point A, we're going to call, I guess the solutions call it FA and FB. So we're solving for that. So FA is going to be equal to mg plus v squared over r, which is 1.60 kilograms times 9.80 meters per second squared plus 12.0 meters per second quantity squared divided by 5.0 meters. And that's going to give us 61.8 newtons. So FA equals 61.8 newtons. Okay, chapter 5, number 45. Part B, determining the normal force at the top. At the top, you have mg going down, the normal force from the rail going down, and mv squared over r going down. So n plus mg equals mv squared over r. Oh, I guess we could put negatives in front of them, but we'll just do it this way. N equals mv squared over r minus mg. We'll just put a negative in front of the whole thing. How about that? When we're done. This is going to be equal to n equals m 1.6 times 12 meters squared, 12 meters per second squared over 5 minus 9.8 meters per second squared. This is going to be equal to negative, that's 1.6, negative 30.4. Negative 30.4 newtons. That's part B. .560 reads, an adventurous archaeologist crosses between two rock cliffs by slowly going hand over hand along a rope stretch between the cliffs. He stops to rest at the middle of the rope. The rope will break if the tension in it exceeds 2.5 times 10 to the 4 newtons, and our hero's mass is 90 kg. So 2.5 times 10 to the 4th newtons. This is T max. And M equals 90.0 kg. Okay, if the angle theta is 10 degrees, what is the tension in the rope? And then that's A, and then B is what is the smallest value theta can have if the rope is not going to break. Okay. Okay, sum of the forces in the X, sum of the forces in the Y. All right, sum of the forces in the X, we're going to have a T cos, some of the forces in the X, yeah, T cos 10 minus T cos 10 equals 0. And some of the forces in the Y equal T sine 10 plus T sine 10 equals, we got to weigh 90 kgs times 9.8 meters per second squared. All right. Let's see, we're going to just go ahead and solve for one. All right, T cos 10 equals T cos 10. So this we call this T1 and T2. T1 equals T2. And then 2T sine 10 equals 9.090 kg times 9.8 meters per second squared. So T is going to equal to 90 kg times 9.8 meters per second squared, divided by 2 times sine of 10. And that's going to equal to T equals to 2540 newtons. Now we've solved for the maximum angle. We're going to go back to this guy. And we're going to say, we already know that the breaking point is 2.5 times 10 to the 4th newtons equals 90 kg times 9.8 meters per second squared. And then over 2, and then sine theta. All right, so let me get some board space. All right. So let's see, I'm going to get sine theta equals 90 kg times 9.8 meters per second squared over 2 times 2.5 times 10 to the 4th newtons. Then we're going to do a sine inverse theta equals sine inverse of this. And I'm going to get an angle of 1.01 degrees. All right, chapter 5, problem 68 says a 2-kilogram box is suspended from the end of a light vertical rope. A time-dependent force is applied to the upper end of the rope, and the box moves upward with a velocity magnitude that varies in time according to V sub t equals 2 meters per second squared times t, 2 meters per second squared times t, plus 0.600 meters per second cubed times t squared. What is the tension in the rope when the velocity of the box is 9 meters per second? All right, so we need to find the time. So we have I'll go ahead and put 9 meters per second here, 9.0 meters per second, and equals all that. So to do that, I'm going to rearrange it. It's going to be 0.600 meters per second cubed times t squared plus 2 meters per second times t minus 9.0 meters per second equals 0. And that's going to be a quadratic formula with t as the variable. And going to my poly solver, let's see, on, clear, boom, boom, enter. A is 0.600. And our B is 2. Enter, and C is 9. I don't like x1, but what's x2? Okay, so let's see. I'm getting t is 2.59 seconds. All right. Now I just have to differentiate and find the acceleration at that time. So dv and dt equals a equals 2 meters per second squared plus 1.200 meters per second cubed times t. And so putting t in there, let's see. Gives me 5.059 meters per second squared. All right, that's A. And once again, like that other problem we did, the tension's got to overcome gravity. So let me erase some of this. T is equal to mg plus A. So T is going to be equal to 2 kilograms plus 9.8 meters per second squared plus 5.059 meters per second squared. And the answer is going to give me 29.7 meters. All right, and that concludes chapter 5.